Today I'll talk about the equation of mechanical energy which can be derived from Navier-Stokes equation. So first, what is Navier-Stokes equation? Momentum equation or Newton's second law of fluid flow. The Navier-Stokes equation describes the motion of viscous fluid flow. In their vector form, they are given by rho dou v by dou t plus v dot nabla v is equal to minus nabla or del p plus mu del square v plus rho and g. So here rho is fluid density, then v velocity vector, t time, p pressure, mu dynamic viscosity, del operator that is gradient nabla, del dot v divergence of velocity vector, del square v Laplacian of the velocity vector, g acceleration due to gravity. So here that top arrow denote as a vector quantity. Now in the Navier-Stokes equation with level term, so if you see the first term rho dou v by dou t, so that is nothing but temporal change of velocity, and then rho v dot del v, so that is convective acceleration term, and then next term this is pressure gradient term, and this term is viscous diffusion term, and rho g that is body force term. Now we know the Navier-Stokes equation. Now we will get the equation of mechanical energy. So if we do the dot product both side of the Navier-Stokes equation, dot product of v with Navier-Stokes equation, so v dot of that left hand side is equal to v dot of right hand side. If we do that, we will get the mechanical energy. Now here I am taking the left hand side, so v dot rho dou v by dou t plus v dot del v. So now we know that v is the velocity vector, vxi plus vyj plus vzk dot then rho dou v dou t plus v dot del v. So now if we do the vector operation and if we open up, so we will get that vx rho dou vx dou t plus rho dou vx dou x vx plus rho dou vx dou y vy plus rho dou vx dou z vz. So we'll get that. So if we do this term with these three things, so we'll get this term, this term, this term, and then if we do this term with this, okay, so we'll get this 9 term. So after getting 9 term, so we have to reorganize, and if we reorganize, so we'll get different things. So let's see. So first we are taking these three terms, is segregate. So this is nothing but this, and other term as it is. Now from here, so we take this on this term only, and then we will see. So this term, underline term. Now we know that vx rho dou vx dou t, so this term vx rho dou vx dou t, so these three term, so we are taking. Now if we can write this term as a this term. Now if we do the partial differential equation for this, so half rho constant, then dou vx square by dou t, so that we can do half rho into 2 vx into dou vx dou t. So that 2 cancel out, so rho vx, so we will get that vx rho dou vx dou t, so we will get this. So now for 3 term we will get 3 different kinetic energy. So now together we can write. So now let's attempt to express this as a time derivative of half rho v square. So this is the half rho v square. So now we can kinetic energy, I can write half rho v square, the magnitude of velocity, so half rho vx square plus vy square plus vz. So we can write that dou t of half rho v square is nothing but dou t of this, and that is nothing but this. So we'll get, so this term is nothing but dou t half rho v square, that is kinetic energy, increase of kinetic energy. So we'll get that this term, and rest of the term, so we can reorganize like that. Different color I put, so and I reorganize. So if I reorganize again, we will get the kinetic energy. Okay, so this is the x derivative with respect to x derivative, with respect to y derivative, with respect to z. So we'll get that. Okay, so now from here we can write, next slide we can write, so this term we'll get this term. So from here if we take that x term, so we'll get this term, okay, y term and z term. So from here we can write this and this, so together we can write, so this together, these three terms we can write as a this term, so this term, so del dot half rho b square the v, and this term as it is. So finally we'll have this left hand side of that dot product of Navier-Stokes equation is nothing but this. Okay, so v dot rho dou v dou t plus v dot del v, so nothing but this. Now next, that v dot that del p, so we can write that velocity vector and that gradient of v, so we can write like that. Now if we do so another, so write out del dot rho v, we write, so that is the del, and then this is rho v. So if we take that dot product, divergence of rho v, sorry, pv, we'll get this, and del dot, so del dot pv we can write like that way. So from that we can get the identity. So finally del dot pv is nothing but this. Now if we take this minus v dot del p is nothing but this. So we can use this equation later stage. Means later stage means when we'll put all together, so we'll get that. So finally this we'll get. Now similarly if we do the dot product of that v dot mu del square v, so you know that tau is nothing but mu, so du by dx, du by dy, so many things, so many tau term is there, so 9 tau term is there. So we can write this term is nothing but v dot del dot tau. So now from this identity, from this identity we can write that t is nothing but a tau. So we can write that tau double product, that double product that is del dot v is nothing but this. Okay, so now we are doing this. Okay, so from this is equal to what? So we'll get that. So from this we'll get this, and this is the identity. Okay, and from that we can write this minus del dot tau dot v minus again minus tau double product then del dot v. Now from here, so we are doing all these things. So from this term we got this term we got this, so this term is this term is this, and this into this term is this term, and v dot rho g, so as this is this term. So now after getting all this term, so we all this we are multiplying with v, means we do the dot product of v with Navier-Stokes equation, so we got this each term. Now if we put all together, so we'll get this big equation. So this big equation is nothing but mechanical energy equation. So now what is that? So first term, that is dou t of half rho mod of v square, so that is rate of increase of kinetic energy per unit volume. Second term is the rate of addition of kinetic energy by the convection per unit volume. Then this term is rate of work done by pressure of surrounding on the fluid. Then this term is rate of reversible conversion of kinetic energy into the internal energy. Then this term rate of work done by viscous force on the fluid. And then this term means this term is the rate of irreversible conversion from kinetic energy to the internal energy. And this term obviously body force related, rate of work done by the external force on the fluid, gravity. So this is the mechanical energy equation, and each term denote rate of increase of kinetic energy, all these things. So in this slide it is described everything. That's it. It is very important for transport phenomena, as well as if you want to calculate the mechanical energy, so you can do that. That's it. Thank you.